Welcome, EE123, lecture 20. Woo! Okay. So while filter design is not my favorite lecture, it is one of my favorite topics. And I enjoy designing filters very much. Announcements. John, there's no announcement, but actually, and I have an announcement. So today, last HEM lecture, but not everyone registered still. Did you? Yeah. Okay. Fine. Not everybody registered, so if you're listening to me on YouTube, please register today to the amateur radio exam. Please, please, please. Thank you. How's Lab 3 going? Who says? Why? Okay. Any technical difficulties that I should know of?
It's not really like a technical difficulty, but it's really like noise. Like you said, like the receivers aren't very good.
Which one? The subcarriers?
No, like our receivers in general, so just even modulating.
No, the FM should be like sweet. Like really good quality. And if you capture it outside, for sure. This is like 59,000 watts effective radiation power, like next to your door. Amazing quality you should get. Like really good. I mean, the one that I played here, that's the quality you should be getting. Maybe your antenna or your gain is not correct. Maybe it's actually overgain. Overgain would saturate the receiver. You might still get a spectrum, but it would be noisy, like really noisy because of clipping. So look at your gain. Okay, the gain that you make sure that the signal is not clipped, and make sure that the signal is not, at the bottom. Like there's no bits. Okay, that's another thing that, and don't do it outside. And if you really want to have a good a good reception, you need some sort of a ground plane for the antenna. So if you put on some metal, like a metal cabinet at the bottom, the reception would be way better. If you hold it in your hand like this, don't touch the antenna, but hold it like this and the antenna on top, that also will improve. Hold it straight. Okay? Don't put it next to like a monitor, which emits up, other stuff. But make sure that the gain is correct. That's the most important thing. Okay, so tip. Okay, if you're saturating, quality would be poor. But the mono should be like you would, except that it's going to be with a little bit of a high, it's going to sound a little bit of emphasizing the high frequencies. And one of the reasons is that we haven't talked in the lab is that radio station pre-emphasize the high frequencies just because high frequencies tend to have more noise when you do FM, and that's why the subcarriers are a little bit more noisy too. And so what they do is they pre-emphasize, so you increase your signal in the high frequencies, and then you're supposed to attenuate it back before playing it. But we didn't do it. Just skip that part. Okay. Yeah. The noise stationary, but not white. Yeah, it's more higher frequency noise. Yeah, and that's because there's a derivative operation. It's really taking a derivative emphasizes high frequencies. Any more questions? Who finished Lab 3? Just so I get finished. Did you get good sound quality? Yeah? Post the gain that you used. And which SDR you used. Because there's two, it's the blue one, it's the not blue one. There's slightly different versions, so it's not the same chipset, if you don't mind. I use the white ones. Filter design? Did you design filters already? You did. You did design filters. But I told you, okay, just design this filter with these parameters. But you didn't really design them then. I designed them for you, and then you ran that application. So today we're going to talk about how to design filters. And one of the reasons is because of the next lab. I think it will be useful to do some filter design over there when we talk about communication. Okay. So linear, first of all the filters we're going to use here are going to be linear filters, non-adaptive filters, and like not median filters. All these are nonlinear filters are really hard to analyze. It is possible to analyze them a little bit, but they're going to be, of course, signal dependent. So when we talk about linear filter design, they can be often described either by a convolution. Okay, so linear shift invariant. It used to be an art. People thought this should be an art. But now there's really lots of tools to design optimal filters. So if you look at SciP and MATLAB and like tons of other libraries exist for you to design digital filters, both infinite impulse response and finite impulse responses. Okay? But the reason I think it's important to understand how to design them is because each design has its own quirks. And although it's optimal, it might be optimal in a certain sense. That may not be what you really want for your application. And most people actually don't use even optimal filters. They'll just use an easy design, which I think is a poor choice to pick something that's just because there's a function, you're going to use it, but then, you might as well just do something a little bit more optimal. Okay, so for DSP, there are really two common classes of filters. And, of course, there are the infinite impulse response and the finite impulse response. And these use a finite order of parameters. Even the infinite impulse response, they have a finite order of parameters, a filter order, so that that restricts really what is possible to do with your design. Okay? So what we're going to do is we're really going to cover deeply the design of finite impulse response filters because now with computers, those are the most easy actually to use, very efficient, and also have really nice properties that we will explore later, which is this linear phase and other things like this, so they don't distort your signal. They don't cause dispersion of different frequencies, so no delays between different frequencies and so on and so forth. So we'll talk about this more when we reach that chapter of the class. But I'll also briefly mention the type of IR filters that exist and what is the concept of how you would go and design them. But then you can, of course, use the tools in order to do so. But we're going to talk about them briefly. If there's really a will here to learn more about IR, I'm more than welcome to talk more about IR as well. But you'll have to kind of like, hey, Mickey, we want to talk about IRs. Okay, so I'll do that. Okay. So what is the linear filter? Okay. Linear filter is going to attenuate some frequencies. It's going to pass some frequencies. And it's going to affect both the magnitude and the phase of the frequency response. Okay? So you have to understand this. It's just not necessarily just the magnitude effect. There are filters, for example, that have no magnitude changes. Like you can pass something through it, and you'll see that the the frequency response is flat. No magnitude effect. But then something that comes out doesn't even resemble something that came in. Yep. Oh, that's English. It's not math. It's not fair. I'm not an English speaker. Affects. How about this? Is that good? Okay. I'm not upset with you, actually. Last name? Mukund? Yeah. Wow, you're ahead. You just beat Angela by $1. You're at 8. I mean, that becomes profitable. Pretty good. Okay. Is that okay? Okay. All right. Affects both magnitude and phase. Now, you see that IR filters actually have a nonlinear phase response. That could be an issue depending on the type of signals that you're going to be. Well, I was talking about something else. I said something about, there's a filter with a constant frequency response, but whatever you put in will come out like mixed and like it doesn't even resemble the input, even though you didn't touch any of the frequencies. Like you didn't really attenuate anything. Is that crazy? Does it happen? Absolutely happens. Have you ever passed light through a prism? Yeah. Is there attenuation, like ignoring the fact that actually there is some attenuation? But let's say there's no attenuation, like through a lens, right? Right? There's not much attenuation through like a lens. But something that comes out is different than something that comes in. Okay? And what happens is that things are delayed differently. Okay? Different signals will be delayed differently, and that would cause them either to focus, disperse, and we'll talk about that. Okay. So IR filters will be mostly nonlinear phase response. And what it's going to cause is some dispersion in the signal. So you put two frequencies in, and then they'll be delayed with respect to each other. Okay? So if you put a kind of a narrow pulse in, it will spread. Okay? It could be, though, linear over a certain range of frequencies, but not everywhere. And so, yes, you can actually use them, but there needs to be, I think, a good reason why to use an IR as opposed to an FIR. I would say that FIR are much easier to control the phase. You can almost prescribe any phase that you want, up to, of course, the order of the filter you're going to be using. And you can also use both linear and nonlinear phase. Okay, so you have this choice, and this is why these are so powerful. So how would you design a filter? Like using the tools that we have so far. Like how would you design a low-pass filter? I mean, you should know that, yeah.
I would make a frequency response or a Z transform, and then invert the transform, and that would give me time limit.
Right. So a Z transform you would want to design? Okay, that works. Okay. A Z transform or a frequency response that you want, and then you would compute the inverse, and then apply that filter, right? Okay. That's interesting. I think it's actually a really nice approach. What if you have some criteria on, like I really want to attenuate those frequencies that much, I want to pass that frequency, how would you then do it? Yeah. You have an ideal one that you want, and then you take it, that was a good suggestion, you take an inverse transform, but now you've got like an infinite filter, I don't know. What do you do then? Truncate it, do something, and make sure that that if you compute the forward Fourier transform or the forward Z, you get the response that you want. Okay? So you do something to it to make it finite order, and then make sure that it meets your specs. Great, this is exactly what we're going to do, but a little bit more, slightly more rigorously. Okay? So there's the most common way or the most simple way of designing FIR filters is through the windowing method. It's by no means optimal. Okay, it's not an optimal, but it's very efficient, very easy to do, and you'll see that most people use actually this type of a filter, even though it's not, there's no optimality criteria there, but it's just easy to design, and they're quite efficient. They're maybe near optimal, but they're not optimal. Okay, so given a desired frequency response that you want, HD e to j omega. What I'm going to do is I'm going to compute, like you said, the inverse Fourier transform of this ideal frequency response to get the impulse response. And then I'm going to get an mth order causal filter by truncating and windowing that frequency response, that impulse response. Okay? So I'm going to truncate it and window it so that it is a finite order. Now, note here that an mth order filter has m plus 1 number of coefficients, or taps. That's the convention. Okay? So just remember this, that an even order filter actually has an odd number of coefficients. This is just to confuse you. Okay? Just so. And the real confusing part is if you design a filter in MATLAB using a window design, there's functions called FIR win. Right? Is that FIR1 or FIR win? I don't know. So, yeah, FIR1, I think. If you design with MATLAB, then you prescribe M. If you design one with SciPy, or SciP, I don't know how you call it, then you actually give the number of taps. So you actually need to prescribe M plus 1. Okay, so just to confuse you slightly further. So it's really important now that you actually read what is the instructions when you, what is the function description, what actually are these parameters if you want to design a good filter. A filter that, as it turns out, if you don't choose actually the right order, if it's even or odd, there is actually consequences if it's even or odd. Okay? Yeah. Yeah, taps is the number of coefficients. Okay. So that's what we're going to do. And so we already saw that the Fourier transform of our discrete or our FIR filter is really the Fourier transform of the desired one, the ideal one, convolved, and I'm pointing out that it's not just convolved, it's actually a periodic convolution between the desired one and the Fourier transform of our window function. So if I have a boxcar rectangular window, which its Fourier transform is described by a periodic sink, then the response that I'm going to get is the convolution, the periodic convolution between this and this, which has a magnitude and a phase, because this is shifted. Hence, the magnitude response is going to look something like this, where if this is the ideal filter, then I'm going to have some passband ripple. I'm going to get some stop band ripple. I'm going to get some transition width, depending on the parameters that I use. And in some application, this is okay. In some, it's terrible. And that's why you need to know something about what the type of filter you're going to be designing. Some application, this is okay. Some application, this is terrible, especially if you've got something that's really like maybe orders of magnitude, higher amplitude just next to your signal and it sits in this frequency, you're not going to be doing well. Maybe you want to move the null over here or something. Anyway, so that's the point. Now, what kind of windows? Hey, we already talked about windows. We talked about windows when we did spectral analysis. Spectral analysis is the other, it's the reciprocal world of actually filter design. Okay, filter design, we want to attenuate frequencies. Spectral analysis, we want to see them. So, yes, all of these, the Henn window, the Henning window, the Hemming window, all of these you can actually use, and we know their properties already in terms of what is their Fourier transform, right? We know that already. And so, again, boxcar has this, really sharp, it's the narrowest main lobe. That means that the transition width of your filter is going to be really narrow, which is a good thing, but at the same time, the side lobes are significant. Hence, your passband and stopband ripples are going to be significant. If you want to taper that off, you can use a Henning or a Hemming window Hamming has equal ripple across the frequencies, which may be a good thing and may not be a good thing. If you want to attenuate frequencies that are really far away, then probably, and you have nothing that's really close, maybe you want to use the Hanning window, because that decays way faster. Okay? But its transition is a little bit wider than, like the second side lobe of the Hanning window is much higher than that of the Hamming window. Okay? So it really depends on the application. And if you want to design a filter, you just go to scipfilter.fir1, and it will design that for you based on your favorite filter. You can actually say, I want to use that kind of a window in that function. So how would you implement that kind of function yourself? What you would do is you first choose the desired frequency response. Okay? And I would say, so here's where students actually get confused. Because there's something that you do from an analysis point of view in order to derive that filter, and there's something that you would do actually on a computer. Okay? So normally it's easy to think in the context of zero-phase filters. So non-causal zero-phase filters. What does that really mean is that when you store a signal, like when you store a signal in an array, then the center, or n equals 0, is in the middle of your array. That's really what it means. But, the computer doesn't know like what's the entry of your array. Like you can think of where is n equals 0 where you want. But it's going to have implications when you compute, let's say, DTFT, which one is like n equals 0. Because then you're either going to get phase, linear phase, or something like this. So that's where people get confused. And so we're going to derive it in a particular way. But sometimes you don't have to do this if you know exactly where n equals 0 and you treat it appropriately. And what does it mean to cut? Okay. Am I going to cut my signal around the center of my array or just the edges of my array? And then maybe I need to do some circular shifting. Anyway, all of this is just the practical implementation of those. But from a derivation point of view, I'm going to choose a certain way of deriving. But effectively, you can implement this in many ways. Okay, so pay attention here. Bear with me, and if you're confused, just ask questions. But that's where I see a lot of confusion. Does it count? Effect. Okay, it counts. Disappointed in myself. Effect or effects? Effects. So you're wrong. Effects. And last name again? Is that your last name? All right, you're third with $6. Fine, I gave him $2. Right. Changed. But no more effect slides. Okay, no more gain on effect. Okay, I announced it right now. Okay. So here's what we do. We're gonna choose a frequency response that actually has a non-causal zero delay, an infinite impulse response. Okay? What does that really mean? It basically means that if I would have chosen like an ideal filter, it would be like a pure sink. Not a sink that is causal and truncated, That's basically what it means. It's not a sink that's shifted positive. It's a sink that would be centered. Because that's easy to design. Then if I need to make it causal, I just shift it. It's not a big deal. Okay? I just, I move the numbers within the array. It's not a problem. But it's much easier than to prescribe the frequency response. Okay. Now, if it's derived from continuous time, if I need to know exactly what the frequency, Then I'm going to choose a t, and then I'm going to choose the omega that I need, and then I set omega over t to be basically W. Okay, so I need to figure out how the real frequencies based on the sampling rate would then translate into a digital frequency, which goes from minus pi to pi. Okay. Then I'm going to choose a window. And the window is going to be a length m plus 1. Order of m, but its length is going to be m plus 1. And that's going to affect the transition width, the type of window, the length of the transition width, type of window, both the transition width and ripple. And what I'm going to do then is I'm going to modulate the frequency response by e minus j omega times m over 2. And that will shift my frequency response by m samples, such that now when I crop from 0 to m, then the middle of my array will have the middle of the sink. Yes? This shifts the impulse response. Linear phase just shifts the impulse response. Yes? Okay. Okay. So now I'm going to determine the truncated impulse response, h1 of n. Okay, so I have h of n, which is the infinite response of the ideal filter. Then h1 is the windowed truncated version of it, which is going to be the inverse Fourier transform of the desired one modulated by j omega times m over 2. That is the inverse Fourier transform again. This comes from the inverse Fourier transform. And then I'm just going to evaluate it between 0 and n, 0 and m. Okay. And then I'm going to apply a window. Now this is effectively applying a boxcar window. Okay. So now I can multiply with some other window, like a Hamming window, for example. Okay, so W could be a Hamming window. Multiplying by h1, these are the same size sequences. h1 is a mth order m plus 1 number of, length of m plus 1. And W is the window of m plus 1. I multiply these, and I get my windowed impulse response of my filter. Simple. Simple method. Now, we don't end here. What we want to also see is what is the effect of this truncation that I've done in the windowing on the frequency response to evaluate that this is actually what I need. Does it fit my criteria? And so now you're going to compute the Fourier transform. And how do you compute the Fourier transform? You're probably going to use an FFT. And you probably not use just an FFT. You should use an FFT over a zero-padded sequence. So you get the H sub W e to j omega well. Okay, so you see what happens between the samples of the DFT. And you need to oversample this by a few factors than the order of your filter in order to really see those changes. Okay, so if your filter is of length m, you should probably choose 5 to 15 times m in order to see kind of how it behaves in between. And it's not going to behave crazy if you, you don't need to do 100 times m. You really just need to be up to 15 because there is degrees of freedom now. There is a restricted degrees of freedom by the fact that the filter is only of length m plus 1, or order of m. Then the frequency response cannot change as rapidly anymore. Okay, like it cannot just be this and then go to infinity and then one sample after that it will go away. No, that's not going to happen because it's a finite order. Okay, so oversampling by that factor will give you the right approximation of the DTFD. Does this make sense? And so people sometimes they just compute a Fourier transform of like the DFT of this. This is not good enough because you don't know what's going on in between those samples. So it's important to oversample. That's where zero padding is important. Okay. Questions? Simple, right? And that's exactly what the FIR win function, or FIR1, does. Okay. So here's an example. We want to design a low-pass filter. How often it's used? All the time. Okay, like used it in the lab like a few times. The desired frequency response is 1, where omega is less than equal to omega cutoff, and then 0 otherwise, right? I want an ideal filter. I'm going to choose M, which is the window length, -1. And then I'm going to take the desired one, multiply by, modulated by E minus j omega times M over 2 to get the Fourier transform of H sub 1. I'm going to compute H sub 1, which is a truncated, regular sink, truncated sampled sink, okay, that is shifted by M over 2. Okay. It's shifted by M over 2. And then, so the book tries to avoid at all costs the use of the term sink, but I like sink. They use just sign over, like there's no sink in the book. And so this is in the book, but you can also write it that way. Okay? If you write it as a sink, you need to also put omega c outside, because that's by the definition how sink is. Okay. Okay, here's the result. The result is a windowed sink truncation. Basically, it's a windowed sink function. That's what it really is. It's a windowed sink. And that's the most common type of filter that you would be using for low-pass filtering. It's a sink windowed by something, by a Hamming window, or by a Henning window, or by any of these. Okay. So if you'd like to design, so that's a low-pass. How do you design a high-pass? Yeah, just design a low pass and modulate it by plus minus 1. Okay, that's a good way to design a high pass. How do you design a band pass? All right, so like modulated by something which is not like between 0 and pi. Okay, somewhere in between. Now, of course, you need to be aware of like what's its width, and because this is a remember that this is a periodic convolution that happens, so the behavior is periodic. So if you shifted whatever shift to outside of pi, it comes back from the other side. Okay, so just remember that. Okay, so you would transform. So now you know how to design bandpass filters. You know how to design, basically you know how to design anything you want. And if you want, so general bandpass, you would either multiply by cosine or sine, or if you wanted to, you can do a one-sided, like you can do a one-sided spectrum too, by modulating by e to the j omega sub omega 0 times n. Okay, that's another option. To do a one-sided filter. Now, I want to talk something about the properties of filters that's not in the book. I think it's really important to learn. Okay, and this is really the characterization of this, of this filter shape by the property called time bandwidth product, and that appears everywhere in communication and in optics even, but for some reason it's not shown in the book. But I think it's a really important concept. Time bandwidth product, or TBW, is a unitless measure, because if you multiply time with bandwidth, they cancel in terms of units. Okay. The time bandwidth product will be, in this case, in the discrete, it's actually a measure that's also used for continuous time signal, where time will be in seconds and bandwidth would be in hertz. But in the digital domain, they'll be in samples and multiplied by digital in order to remove the radians, we take W and divide by 2 pi. Right? So then you've got yourself completely unitless measure. As it turns out, if you actually count the number of zero crossings of a certain time bandwidth product windowed sink, you would actually see that the time bandwidth product is also the number of zero crossings. And so this is a cool thing because, like, you stare at a impulse response and say, okay, I have here 1, 2 zero crossings. So this is time bandwidth product 2, and this is 1, 2, 1, 2, 3, 4, time bandwidth 4, and so on and so forth. Now, what this really means, that measures really if I compute the Fourier transform of this pulse or this impulse response. It has a certain length in time or in indices, and it's going to have a certain bandwidth and frequency. And so it's going to have this property of time bandwidth, right? I can measure this. This is something measurable. But as it turns out, it's also the number of zero crossing, which is really nice. The larger the time bandwidth you pick, the more sink-like it's going to look. The more, ripples you're going to see. So the frequency response will look more like a rect function as being something like not so nice. Okay? That's really what it means. Now, why is it useful? It's useful because I stare at this impulse response. I know it's going to be time bandwidth 2. And I know, because it's time bandwidth 2, and I know how long it is, time bandwidth 2, I know how long it is, I can actually tell you what is the cutoff frequency just by staring at this. The cutoff frequency is going to be 2 divided by 16 plus 1, right? Is that something like that? Right, and then multiply by 2 pi. Like, you can actually calculate what will be the cutoff frequency. And you'll see, yes, this is the cutoff frequency. So just by staring at this and looking at the number of measurement samples, I can tell you what the cutoff frequency would be. It's a good way to get intuitive understanding of what is actually the trade-offs are. I also know that it's not going to be very selective because it's only time bandwidth 2. Okay, so now I'm going to choose time bandwidth 8, but the same length. Okay, so increase the time bandwidth, kept the length the same, something got to give. And the something that got to give is the bandwidth. The bandwidth has to increase by a factor of 4, and lo and behold, it increases by a factor of 4. Okay? Now, because the time bandwidth is 8 and the length is 16, actually the cutoff frequency is exactly pi over 2. Actually, approximately exactly. It's always, it depends on the window, it depends on that. But it's a good rule of thumb. So I stare at time bandwidth 8, m equals 16. I know that this chooses half, pi over 2. Very useful. I want to make it sharper. How do I make it sharper? All I need to do then is to extend the time and extend the bandwidth as well. So I'm going to keep the I'm going to increase the time bandwidth effectively. Time bandwidth 16 would be much sharper. Okay, that's how I make sharper. But because I increase the time bandwidth, and I want to keep the bandwidth the same, I need to, again, something got to give. I need to increase my time. And now it is really sharp. And again, 1632, it's half. Then it chooses pi over 2. Same, but now it's sharp. Okay, same bandwidth. Really useful measure in order to know. When somebody talks to you about a filter or some pulse shape, you can always ask them, what's the time bandwidth? And that immediately you can tell a lot of things about what the frequency response is going to look like. Any questions? Okay, I have a few. So these are the frequency responses of filters. And I'm telling you this is time bandwidth 2 and this is time bandwidth 12. How do you find the length? Mm-hmm. Yeah, so what's the bandwidth? What's the bandwidth for this one? Yeah. No, that's the one-sided. Pi over 6, okay. And so n plus 1 times pi over 6 divided by 2 pi should be equal to the time bandwidth. Okay. So n plus 1 times pi over 6 divided by 2 pi should give you 2. Therefore, the length is 23. And what's the other one? This is time bandwidth 12. And now I'm going to do n plus 1 times pi. That's the bandwidth. Divided by 2 pi should equal 12. And I get, again, m equal 23. Okay, so I can figure out approximately what the length of my filter should be if I want a particular specification. You know, it's really, really helpful measure. Okay. The time bandwidth determines the pulse shape, whether it's more rectangular, like how rectangular it is. So if I pick a time bandwidth 32, I know kind of in the back of my head, yeah, this is pretty selective. Okay, so that determines the transition kind of. It's not really, actually, it's not necessarily the transition width. It's just its shape. Now, depending now on what's the bandwidth, then you would get a certain transition width. Okay, so those have exactly the same transition width, but this one has more bandwidth. For the same bandwidth, if this would be longer, then it would have a narrower transition width. Right? Does this make sense? So they have the same transition width because they have the same length. Okay, that was the reason. But this is more boxy. Hence, if I increase the length, it's still going to look the same boxy but squeezed, and hence the transition width would be sharper. Okay. Okay. So all this design requires analytic computation of the impulse response. Okay. And obviously, you're going to be not going to start deriving those. Okay. So an alternative design would be to use the FFT to draw something that would be desired, and then use the FFT in order to compute the impulse response, and then do the truncation and things like this. Okay? And that's what the function sci_p.signal.fir win2 does on a general filter. Okay? So if you want to design a mth order filter, what you're going to do now is you're going to oversample and discretize the frequency response at p time points, where p should be much, much larger than the order of the filter. Again, I mean, if you want to analyze what would be the frequency response of a filter, you should always zero pad. Now what we're going to do is that oversamples, approximates the DTFT better. Now we're going to oversample the DTFT of our desired filter so that we get a better approximation of it. And we're going to oversample again, 15 times is a good number. Okay. Then you're going to modulate by that desired sampled frequency response. Frequency response by E minus j omega sub k. This is the sampled one. Times m over 2. Omega sub k is really just dividing the 2 pi into p intervals. Okay? That's exactly what a DFT would do, except if you have an mth order sequence, which is m plus 1 length, you would get an m plus 1 DFT. So you want a zero pad more to get. So now we're going to use p sampling. And then we're going to compute h1 of n will be the IDFT of order p, because we have p samples of that h1 of k. Okay, because this now is a function of k. Omega sub k is a function of k. It's discretized. After we do that, we're going to apply an m plus 1 length window that will crop our discrete p-length signal to have only m size. And if we zero pad enough, then our impulse response is going to kind of look like the desired one. It's not going to be infinite, but we can approximate it to be really long and then crop it the appropriate way. Okay, so let me show you some examples. And so there's the function signal.firwin2. You pick the order, n plus 1. Then you need to prescribe two vectors. One describes the omegas, and they're normalized by pi, so they go from 0 to 1. Instead of 0 to pi, it goes from 0 to 1. You prescribe omegas, and then you prescribe the amplitude of these omegas. And what it will do for you is going to perform a linear interpolation between those as for the desired one. Okay, or some interpolation between these values. So what I prescribe here, I prescribe at 0 frequency, I'm going to have an amplitude 1. At 0.2 over pi, I'm going to have an amplitude 1. Then at 0.21, I'm going to amplitude 0. So now a quick transition. At 0.5, now I'm going to have an amplitude of 0.2. So there's going to be a big dip. And then at 0.6, I'm going to have an amplitude 1. And then at 1, which is basically pi frequency, I'm going to have an amplitude of 0. So I should be flat, drop, and then stay dropped, and then climb linearly up and linearly down. Okay. Now there is option to actually prescribe p here as well. What the p that you'd like to calculate, but if not, then it'll just choose one for you. This is the impulse response that you get if you design an order like an order of m equal 29, which is m plus 1 equal 30. This is the impulse response, and those are the frequency responses from m equal 30, m equals 60, m equals 120. And you see that the higher the order is, the better approximation I get to the frequency response. Okay? Yeah? Now here's the difference in actually choosing p. As it turns out, that would actually change the result. So if I choose m to be 14, and I choose p to be 16, which is close, too close, then I would get the blue line. And if I would actually choose p equal to 1,026, then I would get the green line. So there are differences. And the difference is because if you had a boxcar frequency response, right, ideal low-pass filter, what is the inverse Fourier transform of this ideal low-pass filter? A discrete sink. Right? What if I then sample it and compute an IFFT? Would be h of n? What? A periodic, discrete sink. A discrete periodic sink. So if P is large enough, then the periodic sink looks very close to a discrete sink. So a discrete periodic sink looks close to a periodic sink. So that's a good approximation. But when it's not large enough, then it's not. And that's the difference that comes here. Okay. So I want to, in a few words, just say something about optimality, because that's what we're going to talk about on Friday. Normally, you would use a window method, and this is really heuristic design using windowed sink functions, really, pretty much. But sometimes you want to design something optimal. Like you have some criteria on the filter, and you want to design the best filter giving those criteria. And so there you want to design h of n with some Fourier transform that approximates this with some optimality that specifies these specs. And the reason that this is actually different than the window one, because with the window one, I had to prescribe the entire frequency, the entire Fourier transform. I had to describe it and then compute an IDFT. But what if there's places where I actually don't give a, like I don't care. I don't care what's going on there. Maybe that's going to improve. Oh, yeah. Okay. So what if I have specs which, I want this to be flat, I want this to be flat, but here I don't care. I don't care what's there. Now, if I do a window design, I explicitly actually prescribe something here. Explicitly, I do that. But I don't want to explicitly prevent. I don't want to try all options. Right? I don't care. So what I could do is to try to come with an optimization that would find some optimality criteria over a range that I care, that my frequency response and the desired one would be close with some measure. And the measure that I pick going to influence what is the filter is going to be. This is a square, like a mean square error. That could be one. I can also do a weighted mean square error. So I can give more weight to different frequencies. That's another one. But I can also choose something that would minimize the maximum deviation between the two. That will give me a different filter. This results in what's called the equiripple design, or Parks-McCallum algorithm that solves it. But filters would be different. And here's just an example I'm going to finish right now. This is actually from a paper that we wrote related to MRI, actually, where we had strict design on an 11-tap filter that should have a frequency response in those frequencies that needs to be at some value, but in between, we don't care. And this is what comes out of it. Yes, here we had a tolerance, here we had a tolerance, here we had a tolerance, here we had a tolerance. And in between, we didn't care. And so that was the best filter within our parameters that gave this. Okay? And with that, I'm going to finish today. And on Friday, we're going to talk how to design least square filters. Who's taking 127? Who has taken 127? Who's going to take 127? Raise your hand. All of you. All of you should be taking 127. It's one of the most important classes engineering or people in the world should know, is how to optimize things. So take 127, and we'll talk about it next.